computational physics, will be telling us about the exciting results from the ALPS II experiment.
Yeah, thank you very much for the introduction. And yeah, I am from the ALPS II collaboration, and today it is my pleasure to introduce you our very exciting experiment, the Any-Light Particle Search 2 experiment, which aims to generate and detect particles beyond the standard model of particle physics. And I guess that many of you have already heard that we recently started to collect the data. So after decades of preparation, we started to collect data, which has also been like widely reported in the international press. So we are in a very exciting state of the experiment. The focus of my talk today will be the optics of the experiment, so the optic that we use to generate and detect such particles. Before going into the details of the experiment, I would like to briefly tell you why we are building such an experiment. So, as I said, we are aiming to generate particles beyond the standard model of particle physics. So what are those particles? One famous particle, as you know, is the so-called QCD axion. So for the strong force, we have kind of a discrepancy with respect, related to the charge and priority symmetry. So we expect a violation of the CP symmetry, which we experimentally cannot prove. And to kind of come up with a solution for this dilemma, a new symmetry has been introduced, which breaks at lowest energy and leads to a new particle or field, which we call the axion. And this particle, or those particles, have very interesting characteristics. So, for example, they have a very weak interaction behavior with the ordinary matter, which makes them like very attractive candidates for some cosmological observation, like the cold dark matter. So, if those particles exist, and if we can detect them, we might have then an answer to this the question what cold dark matter is made of. Beside the QCD axions, we have also indication from some astrophysical observations, like the tera-electron volt transparency of the universe. So indication that tell us that there might be also other particles that share the same characteristics with the QCD axion, but have a different mass and coupling strength relation. On those particles we call Axion-Like particles. So as I said, one characteristic of those particles is the weak interaction with ordinary matter. So the question is, how can we detect the existence, or how can we probe the existence of such particles? And although they are very weakly, they have a very weak interaction with ordinary matter, there are experiments which can be categorized in principle in three types that aims to probe the existence of those particles. The two first categories are the so-called helioscopes, like the baby Axio and the CAST, and the haloscopes like the MADMAX and ADMX. And those two categories aims to detect the axions from the core of our sun and from the dark matter halo of our galaxy. Those two categories are they are model dependent. So the success depends also on the way how you model the axion source. The third category, the so-called light shining through a wall method, is the method that the ALPS I and ALPS II experiment is based on. And compared to the other two categories, this method is completely laboratory based. So, which means that we generate and detect the axions or the axions-like particles in the lab. which give us a bit of flexibility on the way how we design our our Axion source. On the further course of the talk, I will use Axion as a synonym for Axion-Like particles, so I will not distinguish between those two particles. Okay, before going into the details of the light shining through a wall technique, let me briefly show you why we have built ALPS II. So if you look at the sensitivity of ALPS I and compare it with ALPS II, then we see that we improve the sensitivity by a factor of about 3,000. So the main goal of ALPS II is to improve the sensitivity. And furthermore, we see also, if we look here, that the motivation for ALPS II is, as I said, are the astrophysical observation like the transparency of the universe to tera-electron volt photons. Okay, so how can we detect such particles using the light shining through a wall technique? If we look at the Lagrangian of the axion, then we see that it contains a term that can couple into photons in presence of a magnetic field via the so-called Primakov or CKV effect. How can we make use of that? One simple way to do that is to shine an intensive light source into a wall and surround the light, the beam by a strong magnetic field. With an certain probability, the following can happen. So photons from the light source can interact with virtual photons provided by the magnetic field and then oscillate into an axion, which can then pass the wall. And behind the wall, we can make use of the inverse process. So we let the axion propagate through another magnetic field where the inverse process takes place. So the axion interacts with a virtual photon and oscillate into an detectable photon, which can then be easily detected with a photon detector. Just again, a reminder, the search parameter that we are aiming for, the GA gamma gamma, is mainly motivated by astrophysical hints. So we are aiming for an parameter of 10 to minus 11 per GeV, which corresponds to a mass of less than 0.1 milli-electron volts. Okay, so let's take a look at the parameter that we use for the experiment. As a light source, we have a laser system which provides us about 40 watt. And we have designed the interaction lengths on both sides of the wall to be around 100 meters. For the magnets, we use a string of 12 dipole magnets from the former Hera accelerator. So it's which are superconductive magnets and provide us a magnetic field of 5.3 Tesla on both sides of the wall. And the interaction length is on both sides the same. For the detection of the regenerated photons, we use two different detection schemes. The first one is the so-called heterodyne detector, and the second one is the transition age sensor. In this talk, I will only focus on the het detector because this is the one that we use to take the first data that we use for the initial science run. Okay, so what would be now the photon rate that we get behind the wall if we take this parameter, if we use this parameters to calculate the photon rate? So we know that the photon rate it depends on the magnetic field, on the lengths, on the interaction lengths between the photons and the magnets, and also on the power that we shine into the wall. If you take this parameter into account and calculate the photon rate, then you get something like 10 to minus 13 photons per second, which corresponds to 1 photon every 150,000 years, which is obviously too long. So the question is now, can we somehow boost the process of the photon regeneration on the other side of the wall? And the answer is yes, we can do that by using optical cavities on both sides of the wall. And the parameter that now boost this process are the so-called power build-up factors of the cavity. So the factor that it's proportional to the finesse of the cavity. So a factor which is proportional to the reflectivities of the mirror that we use for the cavities. If we take into account, so this calculation here is made with the GA gamma gamma that I mentioned before. If we take now the power build up for ALPS, so the anticipated power build ups, and calculate the photon rate, then we get something like 10 to minus 5 photon per second, which is about 2 photon per day, which is easier, or which is easier to detect than 1 photon every 150,000, I guess. So it seems that the cavities are quite important for for boosting the regeneration of the photons. Therefore, so let's have a closer look into our cavities. So the cavity before the wall we call the production cavity, and its main function is to increase the power in front of the wall, so to increase the circulating power between the two mirrors, and those to increase the ALPS flux through the wall. For the final science run, we are anticipating a power or a circulating power of 150 kilowatt in the production cavity. On the other side, we have the so-called regeneration cavity, and the main task or function of this cavity is to boost the regeneration of photons. And the enhancement factor that we will have in the end for the science run will be more than 16,000. Okay, so using optical cavities is it's not that easy as it sounds, actually. So we have a lot of strict requirements on the cavity. So what do we need to deal with? So first of all, as you can imagine, the regenerated photon within the regeneration cavity are identical to the one on the production cavity. So due to energy and impulse conservation, it has to be like that. So which means that we have to make sure that the photons or the field from here resonates also here to get a power buildup. And to have to get the anticipated sensitivity, we have to have an overlap of 90% between the two fields, between the production cavity and the regeneration cavity field. So to have a sufficient energy transfer between the two fields, we want the overlap to be more than 90%. And this is contains of two parameters. So the first one is the so-called spatial overlap. So we have to make sure that the mode of the production cavity spatially overlap with the field or with the mode of the regeneration cavity, which means that we have to pay attention to two parameters. The first one is the so-called angular degree of freedom. So we have to make sure that this field is angularly aligned to this one with a precision better than 5 microradian. And the other one is the lateral degree of freedom. So we have laterally ensure that this field here overlaps with this one with a precision better than 1.2 millimeter. And this has already been demonstrated, so we are able to get these requirements. And the other one is the so-called spectral overlap. What does it mean? In principle, it means that we have to overlap the resonance frequency of both cavities. So the resonance frequency of production and regeneration cavity have to have an overlap which is better. Well, the precision has to be better than 1.5 hertz. If we convert that into possible length fluctuation of the cavity, then it means that we can tolerate a length noise of less than 0.6 picometer. Okay. Now let's have a look how we can detect such a low photon rate. So as I said, we have only 2 photons per day. And it's not that straightforward to detect such a low photon rate. And one way to do that is to use a so-called heterodyne detection scheme. So what does it mean? In principle, it means that we use 2 different lasers with 2 different optical frequencies. Now, let's assume that our laser source, our light source, which we call the high power laser, has a frequency of nu1. And the frequency or the power of nu1 that reaches the detector, which is somewhere here, it's quite low. So it's only 2 photons per day. So how can we detect that? One way to do it now is to beat this field with the field of a second laser, which you call the local oscillator, with a frequency of nu2. And by looking into the amplitude of the beat node frequency, we can get access to the power of the power of nu1. So the amplitude of the beat node frequency tell us something about the power that is regenerated, or the power of the regenerated photon within the regeneration cavity. From that, we also see that both fields have to be resonant within the regeneration cavity. So how can we do that? In terms of cavities, it's quite straightforward, actually. So we have to make sure that the cavity length is always a multiple integer of the wavelengths of the laser, or the optical frequency is always a multiple integer of the free spectral range of the cavity, which is defined via C over L. So it's quite straightforward, but how can we technically do that? The way how we need a dedicated control system to do that, and the way how we do that is the following. First of all, we start to stabilize the frequency of our light source, so the high power laser, to the resonance of the production cavity, so to the length of the production cavity. And we use the so-called boundary hole locking technique to do that. And we do the same with the local oscillator on the other side. So we stabilize the frequency of the local oscillator with the boundary hole technique to the length of the regeneration cavity. Okay. Now the next step is we use a third laser. So we have to now to make, so the frequency nu1 and nu2 are stabilized. Now we have to make sure that this field can also resonate here. And the way how we do that, we use a third laser, which we call the reference laser, with a frequency nu3. And the first thing that we do, we stabilize the frequency of that laser by using the transmitted field of the regeneration cavity by implementing a phase lock loop between the reference laser and the regeneration cavity. So the frequency of the reference laser now is following the length of the regeneration cavity. And the final step to ensure that this field resonates in the regeneration cavity is to implement further loop that make sure that the production cavity lengths follow the reference laser frequency. So by doing so, we make sure that if we have regenerated photon here, it resonates within the cavity, so we get a power buildup. Yeah, and so if the loops are implemented, so if the loops are closed and we have a signal on the detector, the signal will then sum up coherently, while if we have any noise signal on the detector, will sum up incoherently. Okay. Let's now take a look at the real experiment. As I said, we are using magnets from the previous Hera accelerator. Here in the dashed white lines, we see the ring of the accelerator, and the ALPS experiment, which is shown in this picture here, it's located here. Okay, so it's the ALPS experiment is in the Hera tunnel, And here we see on the left side here, somewhere here, so it's about 100 meters from this point. This is a panorama of the whole experiment. We have the so-called north-left side of the experiment, where the high power laser, so the light source, is located. Then on the other side, so here is the so-called north-right side, where the heterodyne detector is located. And in the middle, so in between of the two clean rooms, we have the so-called central hall. And here we have the so-called central optical bench located. So the central optical bench contains the end mirrors of the cavity, so the planar mirrors of the cavity. And they are located, or they are fixed to a breadboard with a certain design to make sure that we meet the requirement on the angular and lateral stability, as well as the requirement on the phase stability for the heterodyne detector. Okay, just a brief look into the magnets. So here again, a 3D model of the experiment with the individual clean rooms. And as I said, we use the Hera magnets, which means that we have to straight them. So in order to have a sufficient free aperture for the circulating beam in the cavity, we had to straight the magnets, which I guess is a great success for the engineers. So by doing so, by straightening the magnets, we were able to increase the free aperture from 5.5 millimeter to about 18 millimeter. Yeah, and the magnets have been tested finally. So the straightening was done in 2018. We tested the magnets in 22, and the final safety check was just recently in April, just before we started the initial science run. Okay, what do we use as a light source? As I said, we use a laser which provides us about 2 watt. It's an infrared laser, and we amplify the power of this laser with an amplifier stage to about 70 watt. And in this nice picture here, we see the north left clean room. So in red, we see the beam propagation path, or the beam path for the high power laser, which is shown here. So this box here is in principle this picture. And here is the north left, is the production cavity input mirror. So it's located here in the vacuum chamber. And between the HPL, between the high power laser and the production cavity, we have also a so-called pre-mode cleaner. So it's a cavity that cleans our mode, or our beam, in terms of higher order mode contents. And with that pre-mode cleaner, we can also show that. So this is a mode scan which we took with the pre-mode cleaner, and it shows that the high power laser beam has an higher order mode contents, which is less than 5%. So it's a quite clean beam. Then after the pre-mode cleaner and some losses on the propagation way of the beam, so some losses most likely due to the quality of the optics that we use to direct the beam to the production cavity, we get about 40 watt injected to the production cavity or to the central hall. Yeah. Okay. So as I said, we have like very strict requirements on the stability of the eigenmodes of the cavity, and also on the phase of the signal that we detect with the heterodyne detector. And to meet this requirement, we have installed the planar mirrors, the end mirrors of the cavity, and on a central optical bench, which is shown in this nice picture here. So this is the central optical bench. It's not finalized in this picture at the moment in the experiment. It is finalized, but this picture is not the newest one. And on the left side here, we see one of the planar mirror of the cavity, which is installed in a very stable mount to meet the angular requirement for the spatial overlap. And we also use for some crucial components, optical components, a very ultra low expansion material to meet the phase requirement for the heterodyne detector. In this picture, we see the installation of the central optical band in the vacuum chamber. So it's a quite heavy piece of metal which require cranes to install it into the vacuum chamber. So it took some effort and some learning process. Need some learning process to be able to install the bench into the vacuum chamber without bumping something, because if you have installed the optics, then you don't want to bump something to destroy your alignment. Okay, the next component or the next parameter is the regeneration cavity. So we have demonstrated that we are able to lock the regeneration cavity so over weeks in principle without any breaks. So the scheme that we use to stabilize the cavity is quite robust. And we have also measured a power buildup of 7,000 for the regeneration cavity, which is also the power buildup that we use for the initial science run. Besides that, we have a quite nice storage time, which is about 6.8 milliseconds. And this already kind of belonged to the longest ever measured storage time for such long cavities. Okay, let's now take a look on the setups that we use for the initial science run. So the initial science run has a few modifications compared to the setup that you will use for the actual science run. So first of all, we don't have a production cavity, which means that the power of the high power laser, so the 40 watts, are directly injected to the central optical band. This has some advantages. For example, it makes easier to hunt stray light, so to find the source for the stray lights. And beside that, we have a loop. We have only 3 loops compared to the final design where we have 4 loops, which makes easier to stabilize the system and to investigate the environment that we are working on. Another modification is that instead of aiming for an GA gamma gamma of 10 to minus 11, we slightly reduced that to 10 to minus 10. And this is due to the fact that we are dealing with stray light. So stray light is kind of the limiting factor for the GA gamma gamma parameter. So if we now take this parameter and the power of 40 watt and calculate the photon rate that we expect, then we get something like 1 photon every 15 years. And if we then install the regeneration cavity with the power buildup that I mentioned before, so with 7,000, sorry, then we get a photon rate of about 1 photon per day. Okay, so this is now the setup that we use, or that used for the initial science run, which has started like a few weeks ago. So as I said, stray light is one issues that we are dealing with at the moment. And in this picture, we see again the central optical band, which is installed in the vacuum chamber. And in red, we see the beam path of the high power laser. And here is the path where we dump most of the power outside the vacuum chamber. And to minimize the effect of stray light, we use for some crucial components light tight housing, which is shown here. Furthermore, to reduce the effect of the stray light of the HPL beam, we also use a light tight bellows, which connect the flange to the light tight housing. By doing so this is a plot of the signal on our detector. So don't pay attention to the labels here. Let's just focus on this red graph. So what we see here is the signal on the detector while the shutter is closed. So what does it mean? It means that, so here we have a shutter which kind of is our wall. So we can open and close it remotely. And we close that and measure now on the on the regeneration cavity side on the head detector, the signal on the head detector. And we see that it has a certain level. And if we then install the light by tight bellows and measure it again, then we improve that the level, so the stray light level has improved by several orders of magnitude, so about 3 orders of magnitude. So this is still not finalized, so we are still dealing with some stray light, and we are investigating how we can further reduce the stray light effect to improve our sensitivity. Okay. So with that setup, so with all this improvement and modification that I showed you, we have started to take or to collect data, which was in May 23 or 23 of May. And from what we got from the data, we can already say that the system is quite robust. So we can stabilize the system as I described before. So, and it expects also as it behaves also as is expected. And we got already like several stretches of data with the system being full locked, and each stretch has more than 10 hours of data. So we have in total about 40 hours of data that we need to analyze. But what we already see from the data without a deep analysis is that we have a good phase and spatial overlap maintenance. So the phase maintenance for the signal on the detector and the spatial overlap between the HPL beam and the eigenmode of the regeneration cavity. Here are some nice pictures. This is a picture of our control room. So in principle, what we need to stabilize or to keep the system locked and stabilized are just 3 monitors and a few iPads. This is the optic teams that it's observing the system while it is locked. And here is, among others, Andreas and Axel celebrating the data taking process. And with that, I would like to come to the end and summarize my talk. So I showed you that ALPS is a light shining through a wall experiment that uses superconducting magnets, state-of-art optics, and detectors to generate and detect Axion-like particles. We have recently started to take or to collect data. We have several periods of data that we need to analyze. And the first so the first data that we are getting is with reduced sensitivity, so it's without the production cavity, and the hope is, so we will analyze the data and see what we learn from this process, and the hope is then that we will this year get to the final experiment, to the final sensitivity, so to install the production cavity and to get to the sensitivity that we are actually aiming for. And with that, I thank you for your attention.
Yeah. Plenty of time for questions. Okay. Thank you for the great talk. Make sure that's on.
Thank you for the great talk. Could you mention some of the reasons your production cavity produces higher noise?
Sorry, say.
Could you mention some of the reasons you believe the production cavity produces background?
I don't know if I mentioned that the production cavity is somehow producing any background noise. Actually.
Why you're not using it then?
Sorry?
Why you're not using the production?
Ah, that's your question. Well, for several reasons. First of all, we want to get rid of an additional control loop, which make it easier to stabilize the system. So if you want just to test the environment, then it's easier to make the system as simple as possible. The second one is we to analyze the stray light in the setup. It's much better to have as much as so to have a lot of power in the central area on the central optical bench, because then you can easily track the stray light source with that. That's basically the only reasons.
Yeah, thank you for the very nice overview talk. I had a question about the last slide. So you said that you are taking the data without the production cavity now, and then there will be a full science run later. But will you already, because I think Andreas mentioned that you are planning to already publish something about this initial run without the production cavity. Is that still the plan, or maybe I understood this wrong? Probably I shouldn't. Yeah.
To be honest, I mean, we will see.
Yeah.
I don't want to say we want to publish this data. This data we took for some reasons which are not really important, I guess, for this talk. But I don't expect the data to be published.
Okay. And in terms of the analysis, so since this is slightly different from the ALPS I experiment data analysis, so do you? I mean. Can you say something about that already? How you, what kind of strategy you will have for the data analysis, since it's a heterodyne? Counting.
I mean, I kind of don't know what you exactly referring to, but the way how we will analyze the data is so we use the heterodyne detection scheme, but we are dealing with a lot of stray light. So let's say the shutter is closed and we measure something on the detector and the magnets are on. So how can we make sure that this is kind of a real signal which is coming from the regenerated photons? So what you could do is we just turn off then the magnets and take again a look at the signal on the detector and compare it with the case where the magnets are off.
Yeah. I guess my question was more of how you determine the sensitivity, not in a, in a statistical sense. But I guess that would be okay.
Yeah.
Okay. Thank you.
Further questions? Okay, if not, let's thank our.
You probably mentioned this, so straight light, your main noise background, like your main source of noise. So your straight light, right? So the light that is not supposed to be there because that's why you turn off the production cavity to quantify what is the light that leak into your. Yeah. So apart from this, I'm asking, is this your main source of noise? Is there any thermal noise or other type of noise?
There might be at some point, if we have the production cavity in place, we might have to deal with thermal effects because we have a lot of power in the production cavity. But at the moment, the stray light is the only noise source that we are dealing with.
So you're operating at room temperature?
Sorry?
You're operating at room temperature?
Well, we kind of, stabilize the room temperature, yes.
Okay.
Good question. If not, let's thank our speaker.